In this session, I'll be talking about how do we really build an optimal portfolio using R. So here the expectation is you have a good understanding of the basic features and functions of R. So here our objective is to create a portfolio which can, let's say, minimize the risk. Right? I want to create a portfolio of, let's say, five different stocks. I want to find out in what proportion I have to invest in these five different stocks so that my overall risk is mitigated for a kind of a given amount of return that I am expecting. So it's more of a kind of security selection process. So what securities do I really need to invest in for what kind of return? And how much percentage do I need to really invest in each of the securities? So basically, it's a kind of an optimization problem. So there will be some kind of mathematical models that are involved in building these kind of optimization solutions. But we would be using the same using R. So there are a lot of built-in packages which can perform that kind of optimization for us. So all we need to be comfortable with is how to execute those kind of packages, and once R has executed on the data set, then how do we really interpret the output that is given by R. So this is what we are going to look at in this particular topic. Now moving forward, whenever we talk about a portfolio or optimization of the portfolio, we know that it is primarily based on the concept of correlation between the various products, and this correlation is going to reduce the risk. So depending on what kind of correlation exists between the different securities, we can reduce the risk. If the correlation is very high, probably the diversification will be a very difficult aspect. But the lesser is the correlation between the two securities, we can create a very less risky kind of a portfolio for a given amount of return. So just theoretically, if I have to showcase, let's say I have two securities, right? I have two securities A and B, and I have invested W1 in A and W2, which is 1 minus W1 weightage in B. So if I have to really talk about the variance between W1A and W2B, based on the concept of variance itself, it comes out as W1 squared, the variance of A, plus W2 squared, variance of B, plus 2W1 W2, the covariance that is existing between the returns of A and B. This is the typical formula that exists to compute the variance between the two securities, right? So the covariance in turn is based on correlation, because the covariance between A and B can be written as correlation between A and B multiplied by the standard deviation of A multiplied by the standard deviation of B. So the higher is the correlation, higher would be the variance of the portfolio and vice versa. So basically the variance can be very much reduced if the correlation is very much negative. And we know that the correlation lies between +1 and -1. So if the correlation is very close to -1, I can very well reduce the overall correlation and overall variance of the portfolio, and I can very well take it close to 0 as well. So but in reality, getting two securities with the correlation of -1 is a very difficult aspect. So this is where what is that particular proportion or what is that particular weightage which can reduce the overall variance of the portfolio is what that is very much to be understood. So this is where we will start first understanding quickly the conceptual aspect of it and then putting the same into the R model. So for this I would like to get started with the mean variance framework or the model, whatever you call, which is typically a Markowitz model. So here we are talking about different asset classes or different assets for that matter XI, which are nothing but different securities. So each security, the returns we are taking and we are calling them as XIs. And when I am talking about a portfolio, we are typically talking about different weightages in different securities. And the overall is summed up. So I am trying to invest different weights in different securities in such a way that all the weights sum up to 100% are 1. Now here this particular combination, I can talk of two ways. My combination could be either affine or even convex. Now when I am saying affine, regarding the weights W1, W2, W3, no other restrictions. I don't have any other restrictions in the affine case, but I may put some kind of extra restrictions saying that none of the weights can be negative. So let's say all the weights W1, W2, W3, they all needs to be positive. They can't be negative. But in the affine case, they can very well be negative also, which means we are talking about shorting those particular assets. Whereas here, we are talking of only long only positions, which means I cannot have negative values for the weights. And then, when we are saying we are doing an optimization solution, we are trying to find those possible values of the weights so that the needs of our portfolio are typically met. Our objective of the portfolio is typically met. And generally, the different kinds of objectives people go with. Either they can say, I want a completely minimal risk portfolio. That particular portfolio which gives me the least possible risk. Right? That could be a kind of a requirement. And or sometimes people might look at the maximum returns. I don't bother about the risk, but I want the returns. I expect the returns to be the maximum possible. Or probably in some cases people may define some level of risk, and for that given a level of risk they want the maximum possible return. So that could also be one of the objectives which might be solved through this optimization solution. Sometimes there is a combination. I want my risk to be as much minimum as possible, and I define some level of expected return. So for this particular level of expected return, I want the risk to be as much minimum as possible. So like this, people can create different kinds of optimization problems and try to solve them accordingly using the mathematical or numerical kind of procedures. Right? Now, looking at the theoretical aspect of all these things in a very quick sense, let's say I'm looking at this kind of a problem. I want to minimize the risk. So the risk is measured through the total variance. Right? We have talked about W1 squared, sigma 1 squared, W2 squared, sigma 2 squared, plus QW1, W2, the covariance between 1 and 2. Now the same thing can be written in, so this value has to be minimized. Now in general, this gets written as the minimization of the weights transpose multiplied by the covariance matrix Q multiplied by the weights. Just look at that. So if I talk about weights as W1, W2, right? Then I am talking about a covariance matrix, variance covariance matrix. So in this case here it becomes sigma 1 squared, sigma 2 squared. This is the variances. Then covariance between 1 and 2, covariance between 1 and 2. This is the variance covariance matrix. And I have W1, W2. Or probably I have W1, W2 because this is the transpose. So this is a 1 by 2 matrix, this is a 2 by 2 matrix, and this is a 2 by 1. Now if you multiply all these three, this is what is going to be. Look at this. So W1 sigma 1 squared plus W2 covariance between 1 and 2. And this one is W1 covariance between 1 and 2 plus W2 sigma 2 square. And this I am multiplying with W1, W2. So if you look at it, it's exactly W1 squared sigma 1 squared plus W1, W2 covariance 1 and 2. Again, this comes out as plus W1, W2 covariance 1, 2 plus W2 sigma 2 square. So overall this is what is coming up. Which means in general, I can write it as minimization of the weights transpose multiplied by covariance matrix multiplied by the weights. So this is what I wanted to minimize. This is what is the overall variance for any number of securities. Given the weights are belonging, the total sum of weights is equal to 1. And whatever is the weightages multiplied by the returns is equal to some specified return mu. Right? The way, so I am expecting a mu as a return. So if I don't specify any kind of a return, that's a different thing. But if I am specifying some return, mu is the kind of a return that I want. So this entire thing can be written in a kind of linear equations kind of a form. So the matrix form for all this thing will come out like, so Q, which is a kind of a covariance matrix. So basically if I am talking of three securities, this Q will come out as sigma 1 squared, sigma 1 sigma 2, sigma 1 sigma 3, or covariance 1 3, or probably let me call it as sigma 1 3, 1 2. I call it here as sigma 1 3. Then here sigma 2 1, sigma 2 squared, sigma 2 3, sigma 3 1, sigma 3 2, sigma 3 squared. This is a variance covariance matrix. Then in this you also extend it with ones. 1 1 1. Now you extend it with ones, and then you also extend it with the returns R1, R2, R3. Now these two things, you take the transpose here, so you'll have 1 1 1, R1, R2, R3, and here you'll have zeros. This is the typical form. This would be multiplied with W1, W2, W3 and some other parameters lambda 1, lambda 2, and this would be equivalent to 0, 0, 0, 1 and mu. This is what is the Lagrange's model to model this kind of a situation, which means initially you will have a covariance matrix, then depending on the number of assets you have the ones in the rows, in the next row and in the next column, then you have the returns in the next row and in the next column, followed by zeros to fill up the matrix. That would be your left hand side of the matrix. Then you have your weights. So basically, once you have your covariance matrix, 2 rows and 2 columns are added, right, and they are replaced with ones and your returns, and the remaining values are filled up with the zeros. So this kind of an equation, now you will do it as, this is of the form Ax equal to B. Now if you do the inverse of this matrix, X will become A inverse times B. That is what will give us the optimal weights associated with this particular portfolio. So this is what is the Lagrangian equation. So it's a kind of minimization of a quadratic function. So wherein I'll get into taking, theoretically if I go with, I have to take a derivative, equate it to 0 and all that stuff. But the same thing probably in R, when we work with real data, this problem becomes more and more simplified. So we can see how do we really optimize that kind of a problem using a data set, right? So one thing, let me tell you, just like any other feature that we see in R, there are so many R packages that are available which can help us in doing this optimization part, right? So what we can really do is, first let's get the data and then start doing a step-by-step approach. One, I can use some ready-made packages, but let's see a step-by-step approach so that we can understand how we go forward in terms of doing this end-to-end process of portfolio optimization. So first let's get the data, right? So for that purpose I am looking at a data set which contains the prices, daily prices on the Bombay Stock Exchange of 5 different stocks: Asian Paints, ITC, Tata Consultancy Services, TCS, Hero Motorcar and Yes Bank. And the data has been taken over the last 1 year. from 4th May 2015 to 29th April 2016. So this is the data. I want to take it into R. You can add any number of securities as well. So I want to see what is that particular proportion I have to invest in each of these 5 different securities so that my overall risk becomes more and more minimum. Right? We'll use our optimization solution there. So let me use this variable called portfolio data, or let me use the word portfolio only. So this I want to get from my CSV file. So I'll say read.csv. So I'll simply paste my data, read.csv. So this is the name of the file. So I'm reading this file from this particular location into a variable called portfolio. Okay, so I can very well test out, right, what is the class of the portfolio. It's a data frame. I can really test out first few elements of my portfolio using the head. So these are the first few values of my portfolio, and I can also typically look at the overall structure of my portfolio by using the str. Yes, the first one is a date. Wow, it's not a date. Date is a heading which is showing the format is factor. So better let me convert that into a date. All others are numbers, fair enough. But the first one is looking like a factor. So first thing is I should convert it into a date. So because this is a factor, the first step I'll do is convert it into a character using as character, and after that particular character I convert it into a date using the as dot date and giving the format accordingly. So what I can very well do is I'll replace it portfolio $date. So the portfolio data frame, the date column, I want to overwrite it, wherein first I'll convert that date into a character. So that's where I'll say as character portfolio $date. So this part will convert my portfolio date from factor to character. Now once it is a character, that character I'll convert it into a date using the as dot date, and I'll give the format as. Now here I have the format. First thing is the date, so I'll give %d, then I have a hyphen. The month is in an abbreviated form. Text abbreviated is %b, and then the year is a 2-digit year, so I'll put it as a small y. So this is the format in which I have my date. So I am replacing the existing date with a new date. So now let me try what is the structure of my portfolio. Now the structure of the portfolio is showing the date is of the format date and not the type factor. So this is the first step, or this is the simple cleaning process that I am looking at, especially seeing the internal structure of the entire portfolio object. So here I have a date column, and I have 5 different prices, five different asset prices: Asian Paints, ITC, TCS, Hero Motorcorp, and Yes Bank. So this entire thing is assigned to a variable called portfolio. Then for my working purpose, I will not have the first column. So let me take out the first column. So that's where probably I'll create one more variable, right, called stocks, wherein I'll take my portfolio, but I'll take a subset of it. I'll take all the rows, but I'll not include the first column. I mean, I'm creating a different variable because probably at a later point I may want to use the first column also. So that's where I have created a new data frame, which is a subset of the original data frame without the first column. So that is what I am calling as stocks. So now if you look at the head of stocks, you should not see the first one. So it's only the 5 different stocks. Fair enough? Then I would like to compute. See, all this portfolio concept runs on the returns, not on the prices. I have to typically compute the returns and not the prices. So I'll compute the geometric return or continuous return. So this is what we are looking at, using the logarithm to compute the return. So basically I can talk about the P2 by P1 log. The today's price divided by the yesterday's price and the logarithm of it. But I'll not take it for the first value because I'll not have the yesterday's value for the first one. So that's where I'll say take the tail excluding the first one and divide it by the head excluding the first one. Right? So that is where I'll say the returns. I'll call this as returns, wherein I'm taking the logarithm of the tail. I'm taking the tail means from the bottom. From the bottom, all the stocks except the first one. Right? You take the tail of the stocks except the first one, divided by the head of the stocks except the first one. See, tail gives you the last few values. So head gives you the first few values. That is what we got here. So we say get the head without the first column, get the tail without the first value. So you divide. Right? Don't divide the first one. And once you divide it, after that you compute the log. And that is what is giving me the return. So probably if you really want to look at the head of the returns is coming out as this for all the stocks. So it is basically the logarithm of P2 divided by P1. So this is how we got the returns for each of the stocks. Then, now that we have created a Lagrange model, right, as per this Lagrange model, I first need to find out the covariance matrix, and after that I have to add ones, after that I have to add the returns. So this is what we were talking of, right? The same procedure we will try to build, and then we will try to get into the optimization process. First, now that we have computed the returns, I'll talk about computing the covariance. So let me create a variable called Q. which will hold the covariance of the returns. Simple. COV is a function that will compute the covariance of the return. So I can really find out the head of Q, what got into Q. So this is the kind of variance covariance matrix. With a simple COV, we have got the variance covariance matrix associated with these 5 securities. Then I also need to add ones, right? As per the model, I have to add ones. So for that, I need to find out how many columns are there. So this is where I am creating another variable called n, which will compute the number of columns associated with my stocks. Okay, now n has given 5. So there are 5 columns associated with the stocks. Similarly, for each of the stocks, I can get the average return or the mean return. So I'll capture it in a variable r, the mean return. So that's where I can directly use col means, which is the means of the columns, which you might have seen in the matrix operations. The column means function I can directly use on the returns. Okay, so I got for each of the securities, these are the returns, these are the daily returns for each of the 5 securities that we have taken up. Now this is where my work starts. I have to take the variance covariance, after that append it with ones for those many rows. So I have to repeat the ones number of columns times, and I have to find out the column means for each of them. So these are the things I want to do a binding. So which means I am creating one more. So I am updating the Q now with a Q1. And what all does this Q1 contain? I am doing a row binding. First thing I'll have the Q itself. Then I'll repeat 1 n number of times. N is the number of column type. So first thing is I have the variance covariance matrix. Then I have ones coming up 5 times. So that is what I am calling as repeat ones 5 number of times. And then I am also talking about the returns for each one of them. So this is where I am using the column means directly, so which I have captured in R. So my Q1 is typically looked at like this. So my Q1 becomes all these 5 securities, then ones are added, then the returns are added. Now what I'll do is, I'll take these two. So which means I'll take the tail. Tail will give me the last few, right? So what I'll do is I'll take this tail to last few. So I'll take tail comma 2 saying get the last 2 values, and I'll transpose them here. So which means I'll get them as 2 more columns here, right? And now these 2 areas I'll append them with zeros. So this is where my Q1 gets another upgradation, wherein I'll take the original Q1. Now I'll start the column binding operation. I'll take the original Q1, which is this one. Then these two are typically being transposed. So I'll take the transpose of T is the transpose function, right? Or probably first let me do the row binding of them and then do a transpose. So I'll do a row okay, I'll do if I take the transpose of this one Q1, or probably I'll take the tail of Q1 and the last two rows, right? I'll take the tail of Q1 last two rows, and this if I am doing the transpose, then I'll get these 5 here, right? So basically it comes out like 1 1 1 1 1 R1 R2 R3 R4 R5. Now this I have to put them as zeros and do a row binding to it. So basically I am doing a row binding here. So I'll say R bind of this transpose, and along with that I'll use a matrix of zeros, 2 rows and 2 columns. So this is what will give me my updated Q1. So now you look at the updated Q1. This contains the original variance covariance matrix. Then you have ones, and then followed by the returns of each one of them. And you have the transpose of ones and the returns. And finally everything is filled with zeros here. So this is what was our original Lagrange equation, the matrix form of the left hand side stuff, right? Now I can typically, if I am doing it for ones, I can set some kind of a return, right? So this is my original covariance, the left hand side of the equation, right, based on the Lagrange theorem. And then I can very well go ahead in terms of setting what is the right hand side. So here it is like this entire thing multiplied by the weights W1, W2, so on, lambda 1, lambda 2, and this entire thing is going with 0, 0, 0, 0, and you have 1 and mu. So this mu is what we are calling as your expected return. And because it's a daily data, right, if I am talking about a monthly return or yearly return of, let's say, 10%, I can very well take 10% divided by 250 approximately, giving me 0.4% as my daily return. So probably I can very well set my mu at around, let's say, 0.004 or 0.005. So that is the level of daily return that I really want. And now we have already seen, if I have to build the right hand side, initially I need to have these many zeros and then followed by 1 and then my mean. So this is what I am creating the right hand side, storing it as a variable b, wherein I am doing a repetition of 0. How many times? The number of columns times. So number of columns we have already captured as n. So I am repeating 0 n times, followed by 1, followed by mu. So we have a b which is containing these kind of values. So now I have this particular thing called as a, this is x, this is b. Now this is where I can get my x, which are the weights, as a inverse b. And solving this matrix inverse is through this solve function. So I can say solve q comma b or q1 comma b. Now I got my result. So it says in Asian Paints the weightage is 1.197. Then ITC, it's a shorting. There is a selling that is happening, minus 2.987. Then TCS also, it's a short, which is minus 2.924. Then you have Hero Motor Car, which is a long position, 5.66, and probably Yes Bank is also a small long position of 0.05. So if you add all these weights, it will definitely come to 1. So it's as good as saying you short 298% of your invested money, you short in TCS, again you short 292.4, sorry, in ITC 298%, and you short in TCS 292%. Use that proceeds, out of that proceeds invest 119% in Asian Paints, 566% in Hero Motor Car, and around 5% in Yes Bank. That is the portfolio that will give you the least amount of return for your expected level of risk. So that is how you really get into your portfolio optimization process. So this is the ideal combination of the portfolio that you need to get in case you are looking at investing in each of these securities. But if you say no, I don't want to get into short positions and all, so you can ignore these two and you take the weightages of these three and you put your investments accordingly. So you can very well talk of 1.19 divided by 1.19 plus 5.66 plus 0.05. So that is the proportion that you will invest in Asian Paints. Similarly in Hero Motor Car and Yes Bank. That's one more way of looking at what proportions need to be invested in each of them. But the other way to look at is, now I chose the mean as 0.005, but I can have different combinations, right? My means are ranging anywhere between this to this, right? My means are probably, yeah, it is ranging from 0.0004. So from minimum value to maximum value of this, the means could be almost any value. So this is where I can talk about different possible combinations of the mean. Right now that none of the means are around 0.005, all are much lesser than 0.005. That's where the process talks about shorting in big numbers so that you can very well meet up to the requirement. Whereas I can very well create some kind of a situation, right? Different possible means. So I call them as possible means. I'll take the possible means and I'll take right from the minimum value to the maximum value. So I'll create 100 different possibilities wherein I'll start with the minimum value of R and start and end with the maximum value of R, and I'll take, let's say, 100 different values between the minimum and the maximum. So if you just check what is given by the POS means, right from minus 5.67% to plus 7.98 into 10 to the power of minus 4, you see 100 different possible values in increments. Now what I'll do is, for each of these possible returns, I want my system to compute what is the risk that is involved. So for that I am creating another function, right, which is called as the portfolio variance. I'll call it as portfolio variance as a function, where I'll try to do a apply to each of the individual elements using the S apply, where I'll take the means for each of the values I'll take each of the possible means and I'll create a function. Right, I'll create a function that will apply to each of these particular means. So I'm creating a function which would be applied to each of these possible means, wherein, see, when I'm doing the head, when I'm doing the solving, these are the values that are coming up and these two are redundant. So when these two are redundant, it's better that I omit these two. I have to consider only up to here by solving. So this is where I talk about head in terms, I'll take the head function. I'll take the head function and remove these two aspects. So this is where I am creating a variable called y. Right? Normally what did I do? I'll take solve q1 and b. This is what we have done. So probably let me create the b again. I'll create the b this time as c. So I have to repeat 0 n number of times and followed by 1 followed by x. X is my for different possible means. So I'm creating one b with that, and then I'm taking only the first 5 values of this solve. I'm solving it and I'm taking only the first 5 values. So that's where I'm using the head function of the solve between my q1 and b, and I'm taking only the n values, which is the number of columns. So I'm taking only the first 5 values, which means these are the 5 values which are the weights. Now this weights I'll have to multiply with my covariance matrix, and that again I have to multiply with the weights. So this is where I am simply talking about matrix multiplication. The y, I'm doing a matrix multiplication, which is this. I multiply it with the variance covariance matrix, and again I am doing a matrix multiplication with the same y. And this is what is a simple function where I am typically created the possible returns right from the minimum value to the maximum value, and for each of the returns I am trying to compute the portfolio variance. For each of the possible expected returns I am doing that solve which I have done above and trying to compute the portfolio return. So this particular portfolio returns I can do a simple plotting so that I can see how the returns and the risks are typically vary. So I'll typically look at the portfolio variance for each of them. I'll call portfolio variance. I'll take the plot of the portfolio variance for each of my possible means. So these are the things, x and y. So I'll try to create portfolio variance and the possible means. So this is the kind of graph that I'm getting, which is what I'm calling as the return risk graph, the risk return curve, or otherwise also called as the portfolio frontier. So for different values of the variance, I'm looking at the means, right? So for different values of variance, I'm looking at the possible means. So if I'm ready to have this much of risk, I want to look at these are the possible returns, right? So I obviously, if I'm ready to take this much of risk, I would require the one that is giving me the maximum possible return. I will definitely not look at the one that is giving the least possible return. So what happens is all these points which are giving me minimum lesser return for a given amount of risk, and there is another alternative which is giving me a higher return for a similar amount of risk. So obviously all these possible combinations of risk and return are inefficient. So only from here, as the risk is increasing, the expected return is also increasing. We could see here, as the risk is increasing, the expected return is also increasing. And that is what, from here till upwards, that is what we are calling as the efficient frontier. So whenever we are choosing a portfolio, we have to make sure that that particular portfolio is on the efficient frontier only. Wherever, whatever is the combination of assets that we choose, depending on our risk appetite, we'll have to choose that particular combination which will maximize the returns for a given amount of risk. So that is what we can accomplish through a manual process, right? Just understanding is very much required. So our selection of the port, if I am saying these are the 5 securities that I need to use, then depending on my risk appetite, I will choose that appropriate combination which will give me this kind of a return. Now the same thing in a much more efficient manner or in a much more time saving manner can be implemented using the different R packages. And out of that, the package which I really felt is more and more beneficial is a portfolio package. It contains different kinds of methods which I can directly apply on the time series data. Based on the time series data that I have, I can directly implement a few functions from this package to create an efficient portfolio. So for that, what I'll do is, so I'll typically load this package called time series, right? I'll use library time series. So I'll load this package called time series. Now I'll take my original data, right? My original data was called portfolio. So that is what I'm going to take. So I'll call it, I'll convert it into a time series. So I'll give the same name portfolio, but I'll take it as a time series now. Earlier it was a data frame, right? So just for your understanding, let me look at the class associated with portfolio data that we got originally. It's a data frame. Now I'll try to convert it into a time series. So that's where I'm calling portfolio. I'm recreating, or I'm overwriting this variable called portfolio, which will consider, which will convert it into a time series, wherein first I'll take portfolio from column number 2 to 6. So I'll take all the rows and I'll take 2 to 6 columns, so which contains the values of the assets, and then I am specifying which column contains my date or time. So this is where I am talking about portfolio of all the rows and the first column. So this is the one that contains, so I am talking about time series. This is the data and this is the date part. So this is where I have converted it into a time series. So if I am talking about class of portfolio now this is converted into a time series data type. So if I have really converted into a time series data type, I can use some of the functions that are there in the time series package to compute the returns. So the return in the time series package can be converted directly using a lag function. I don't need to say tail minus 1 divided by head minus 1. That is what we have done earlier to find the return. Now I can very well find out the returns either using that kind of scenario. So I'll simply say returns, and I can find logarithm of, so if I have to take one period before, I'll say lag of portfolio divided by portfolio, which is nothing but the previous divided by the current. So if you look at the head of returns, so these are the returns that are coming up. I don't have the first one. Or I can simply use, we have a function also called returns. So probably I'll call it as stock returns. Let me call it stock returns. I'll use a simple returns function associated with the portfolio. Associated in the time series package. So I can very well see my returns which are coming out as stock returns. So you could see the similar kind of implementation. Of course, you will have the first row showing as NA. So probably you can very well eliminate your first row from the data. Then so now that we have the returns data, if required I can do a charting. I can get the cumulative returns, right? I'll take the cumulative returns based on this return data that I have. So I'll take the stock returns. I'll try to plot for each of the 5 securities. Okay, so the function is not available, so it has to be loaded from a corresponding package. So this function is actually present in a package called performance analytics. So let me load this package called performance analytics so that I can use this function from that particular package. So I'll use chart.cumulative returns stock rate. So yes, I got a plot for each of the 5 securities. I got the returns associated with each of the securities right from the beginning, right from May 2015 to April 2016. So this is just for observing how has been the pattern of the stock returns over the past few periods. So now that I have my time series data, I'll use this F portfolio package to really create this efficient frontier. What we have created earlier, I can create this efficient frontier in a more colorful manner. So I am loading this package called F portfolio. This F portfolio package typically contains those kind of okay, so F portfolio package is loaded. So I can do a simple plotting of the portfolio frontier. So I'll typically call portfolio frontier of stock returns. My return data, I want to construct the portfolio frontier. So this is what the portfolio frontier function will do. It's a covariance, mean variance portfolio frontier, minimum variance portfolio frontier. So it has been solved using solver quadratic programming method. The estimation that it is used is covariance estimator. The optimization is done for minimum risk. The constraints are long only. In this portfolio frontier function, we'll Look at, so it's a long only that has been implemented. So there is no shorting in this case. And what it is being said is the portfolio weights. These are the portfolio weights that it has put, ITC and TCS. I mean, these are the different portfolio weights, and so it has taken 5 different points for the workout, and these are the target returns that it has come out. So this is the kind of overall frontier that we are talking of. So what we can very well see is we can plot this portfolio frontier. So this is a very interactive kind of stuff where I can choose. One means it will plot the frontier which we have got earlier. Then it can add the minimum risk portfolio to it. So this is the most minimum risk kind of a portfolio. Then if I put 3, it will add the tangency portfolio. For each of the single assets, for all the 5 assets, it will plot the risk and returns associated with all the 5. So you could see one here, one here. So for all the 5 assets, it is plotting my risk and return. Then if the portfolio is equally weighted, this is the kind of expected risk and return. And if I am looking at 2 asset frontiers, all the 2 asset frontiers it keeps adding. And then it also simulates, if you want, a Monte Carlo simulation is performed to identify different risk and return combinations. And finally the Sharpe ratio also could be added, which can tell you that this is the point where the optimized or maximization is typically occurring. Right, this is the tangency portfolio. Right, the tangent and your efficient frontier is a tangent to this tangency portfolio. So this particular portfolio is the most efficient or effective kind of a point. So that's how we can very well go ahead in terms of understanding what is our minimum variance portfolio, and based on that typically finding out what proportion I have to invest in each of these securities. And if I do a 0, I am going to exit. But if I really want how much to invest in each of them, then I can also talk about, right, just like a portfolio frontier, I can even talk about efficient portfolio of the stock returns. So you see, based on the stock returns that I have considered, if I want my efficient portfolio, it says yes, you invest 20.3% of your money in Asian Paints, 18.83% in ITC, 44.58 in TCS, and 16.23% in Hero Motorcar. That is the most efficient portfolio. But at the same time, if I want minimum variance portfolio, min variance portfolio, if I want the minimum variance portfolio, I can simply say get the minimum variance portfolio of the stock return. So in this case 2018, again this is the minimum variance portfolio itself. Now if you want to change the algorithms, you have to give your portfolio specification. This is a default implementation. No, if you say no, I don't want the default implementation, I'm fine even with the shorting and all those things, then you have to specify. So if you look at efficient portfolio, if you are trying to question this, You will find efficient portfolio, data, spec equal to portfolio spec. So if you want to change the port constraints is what you can specify. Either you want to give long only or even short. So those are the kind of specifications you will have to give. So if you say I'm going with efficient portfolio, wherein I'll set spec equal to, I'll take it as portfolio spec, and the third one I would also give the short, right? Constraint equal to, instead of long only, I can give it as short. Then also the weights are not changing, right? These are the weights in all the cases, or whatever is the constraint that you are giving. It says don't invest anything in S bank, but invest these kind of amounts in each one of them. But if you change your solver mechanism, because here the solver is R quadratic programming, whereas you can very well set, probably you can say, let me try this, let me put spec is portfolio spec, sorry, portfolio spec, and we can set the solver for this spec. I can set it as solver short. Instead of saying solver quadratic programming, we have different kinds of solver algorithms. So I can say solver short exact. Let me try using this solver short exact, and probably if I want, I can give a minimum return expectation if I have any. Otherwise, let's see, efficient portfolio. Obviously, there will be only one efficient portfolio. So I can very well go with stock returns. Then I have my spec, and I also have short. So here the weightages are slightly changing, right, based on the algorithm that I have chosen, the solver type that I have chosen. The weightages have slightly changed. Here the Asian Paints is 22, ITC is 19. So you can very well use different kinds of algorithms and different kinds of positions, long or short. If you are going with long only, then you don't need to do any kind of modifications. But if you want to go with short, use this solver specification. If you use that specific solver specification, you can even get into the shorting. And one more thing that I wanted to add here before we conclude this. Let's say if I am also using a risk-free asset and I am combining it with this 5 stocks. So for this 5 stocks, you have the variance covariance matrix, right? Now what will you do is, for this risk-free asset, we assume that the risk is 0. That is obvious. So which means when we are creating the left hand side, we create 3 new rows. First we put the zeros, then we put the ones, and then we put the returns. The same earlier process, if I have to repeat it. Then here also we do the same. So we replace it with zeros, but we also take a 0 here. So which means we'll put 1 here and we'll put the return of the risk-free asset, which is the risk-free return. and after that we pump in, we take the transpose of this as well as the last row, and these four we replace them with zeros. So it's like one additional row that is getting created. So number of assets are becoming 6. The sixth asset is a risk-free asset whose variance and covariance are being shown as zeros, and after that the whole process remains the same. So if you are bringing in the risk-free asset also into picture, this is one important point that you have to consider as a part of your building of the portfolio. So this package F portfolio, you can start exploring it in much more detail to really help you to come out with different kinds of optimization solutions that you can create on the set of assets for yourself, right? So this is what I wanted to take up as a part of the portfolio optimization of the securities. If you have any further queries, you can very well get back to me by giving me a call on the number provided below, or you can even send in an email at vamsidhar@pacegurus.com. Thanks a lot for listening to this session. Thank you very much.